Brazilian Agricultural Research Corporation, the Embrapa, Brazil, Embrapa Food Technology. And we have working with quality systems for several years. Okay. Oh, how to evaluate results in laboratories of food analysis? This is one big question when we start to measure and to evaluate measurements we obtain in laboratories. Laboratories have to prove their skills when making analytical and bioanalytical measurements. To do so, standards must be followed, such as BS, ISO, UE, and others. But why some results do not meet their expectations? Some results fall outside their expectations. And therefore, what? We ask, why this happens? Other results do not agree with those already published or previously obtained. However, there are standards and calculations methods to be followed. Thus, we also ask, have the results been calculated according to the standards? Have they been acquired by good laboratory procedures? Have the calculation been verified? So these questions need to be answered, and we have to study laboratory conditions. And as we have this type of results, the first suspects are outliers or uncertainty, a big uncertainty. Well, one of the possibilities suggested is the existence of outliers. We can say that they are results which differ from the other, as you may have seen before. Could these values, in fact, interfere in the routine of laboratories? How much could them affect lab routine? How much are they valid? Therefore, our work was intended to check this out. To this end, we used previously published collaborative studies and validation parameters in the checking. Exploratory and descriptive plots were integrated with statistical tests, and we intend to show here how we studied them. Well, we have here the lipid content percent in one sample, where 11 laboratories were measured, and they measured the sample twice. This is an example from Yildiz Steiner in Hamaker, 1986. We have three plots here: the normal probability plot, the blocks plot, and the Stannon leaf plot. In the first plot, we can say some closeness of one straight line, but at its ends, I don't know if you can see here and here, and at the ends of this straight line, some points had not fit well. The second plot showed no outliers. There is no data at the left or the right of the graphic of the box plot. The third plot shows a region where results are concentrated. They are concentrated in the upper part, and it have a long tail. But we could not conclude about the presence of the outliers in the data. Well, in the table 2, we can see statistical tests for outliers in this example, this previous experiment from Yalden and Steiner. The sample used was one unique sample, one homogeneous sample. The values that could be outliers were 20.4 and 22.0. The common tests are Dixon, Grubbs, and T-student for outliers. The Dixon tests indicate the absence of significant outliers. The same was observed by Grubbs, and the robust score Z here, ZR, did not indicate any outlier. However, T-student did not corroborate them. Finally, Hempel test had not indicated any outlier as well. In short, no outlier was found in the plots of tests and robust score. Therefore, these results confirmed those published concerning outliers by the researchers Yalden and Steiner. In the figure 2, we repeat the plots used before. We have the normal probability plot, box plot, and stand and leaf. And the same laboratory. No, excuse me. We now are talking about one experiment for unsaponifiable matter percent, where we used 10 labs, 2 slides of each sample, and it's presented by ISO 3596 per 2, 1988. Well, this experiment brings some relevant information. In the sample 1, part A, we can see that data did not fit well to the normal probability plot. We can see in the part A, sample 1, that the data do not fit well to the straight line presented here. Both box plot and stem and leaf presented 0.51 in box plot and in stem and leaf as outliers in sample 2. Now, 2 outliers in sample 1, we had a same agreement, but the outlier in sample 2 did not agree with those results published by ISO. So, as this was a collaborative study, we have to think about experimental design models. Experimental design models must be seen. The simplest of them is Y is equal to me plus E, where Y is the measurement, me the average, and E the error. E may be positive or negative. In the second case, we have more complex designs. y is equal to x beta plus e, where y is the vector of measurements, x the incidence matrix, beta the vector of coefficients, and e the vector of errors. But model properties have ever to be checked. It's not enough to make the experiment, but we have to check it. Well, applying the model, we can make it by studying the residues of the model. In the figure 3, we have the residues percent in collaborative study for unsaponified matter in ISO presented before. Well, in the normal probability plot, we can observe one curve. There is something strange in the first plot. In the box plot, in the right, we can see a lot of data out of the plot, out of the region formed by the box plot, the center of the plot, the mean of the plot. Okay. This was precision experiment, and this is model diagnosis. It's little known quality, and it's usually partial when performed. Then we are seeing a little more about it. In this case, we have something strange in normal probability plot and in the box plot. Well, these results were not in agreement with those published before. We had here many outliers. Well, let's see other figure. When examining standard list of the residues in collaborative, excuse me, there is a sound here. When examining the figure 4, the figure 4, the standard list of the residues in the collaborative study for unsaponified matter presented before, we had seen a lot of outliers before. And here we can see this part in red, a lot of outliers just in the lower part of the figure. Well, in this case, we have some discrepancies with ISO and comparing this with ISO. In table 2 here, outliers in graphics for unsaponified matter in ISO experiment. We have here the statistical tests, the results of the plots. In normal probability plot, in sample 1, we have several outliers. Sample 2 known, sample 3 several. In box plots, only 2. One in sample 2 and 2 in sample 3. In a standard leaf, we have 2 in sample 1, 1 in sample 2, and 2 in sample 3. The published outliers were 0.78 and 0.89 in the first sample, known in sample 2, 0.41 in sample 3. But in residues, we had several outliers in both these plots. So we had not agreement with the results of ISO experiment. The statistical test made for unsaponified matter in the collaborative study of ISO showed that for sample 1, the tests did not conform. By sample 3, the same had happened. Using the ZR, the robust Z score, we can see many results which are suspect. Using the sample test, 0.551 was seen as outlier for us. We had twice 0.89 and 0.40 and 0.41 as outliers, significant outliers by sample test. In the residues, just 4 outliers were confirmed. Well, these discrepancies happened when comparing these results to ISO 3596 per 2. Discrepancies similar to these were observed in other experiments at the end of our review work. Several tests did not conform with the previously published papers. Thus, we have the conclusion that non-conformity of outliers was found in collaborative studies. Descriptive graphics can bring useful outliers and distribution information. Dixon, Grubbs, and T-student tests results did not agree with those of ZR and the sample test. And the same happened in other experiments. Only common statistical tests do not fit well to detect outliers in analysis of food, chemical, and biochemical components. Now we have a figure showing which are outliers. Now, we have to start to study other properties, other parameters we use in food quality. We studied uncertainty in published proficiency tests. Firstly, let's think about the definition of uncertainty. Iraqan Sitak defining using the international vocabulary of basic and general terms in metrology. The definition is a parameter that characterizes the dispersion of the values that could reasonably be attributed to the measurement. This may be a standard deviation or a given multiple of it, or the width of a confidence interval. In Iraqan Sitak 2012, the same definition is used, and they say that it comprises many components. The definition of NIST semantics is that uncertainty is a measure of the goodness of result to judge the fitness of the value as a basis for making decisions relating to safety or scientific excellence. Therefore, we can conclude that uncertainty is quantity and it's estimated by a statistic. Well, we used some proficient tests to see what happens with uncertainty. These PT schemes are from FAPAS, AOCS, and other. We had some food components here in this graphics, in this figure 5. We have the uncertainty for ashes, uncertainty for crude fiber, and sodium, all of them in percent. In the first plot, we can see that something opens, something happens at the right. Along the axis of ash percent, the uncertainty does not seem constant in the axis. Something strange happens for uncertainty along crude fiber percent. It seems that something opens. Is there a fan shape in crude fiber? In sodium, does sodium percent uncertainty applying an upward curve? So we had seen something strange in the uncertainty in PT schemes. Well, now we have studied some matrix, some proficiency tests, some proficiency schemes for total aim obtained within 26 months. You have here the matrix, rye flour, extruded cereal, canned milk, condensed milk, porridge eats, wheat flour, canned meat, safflower, milk powder, a lot of matrix. Here, the certified average and the certified standard deviation. By excluding methionine, which was an outlier from the other, and using the estimated certified standard deviation of the total NPT schemes, which are uncertainty estimates against their certified means, we have the plot following. This plot is somewhat like that we saw earlier for ashes, and it looks a bit like those obtained for crude fiber and sodium percent plots. Now, in figure 6, we can see the plot for total N certified standard deviation per certified averages of total N. Look in this figure, it looks like there are straight line parallel to certified averages in this plot. But in this part, it looks that something strange happens. This looks like the figure for actions and the figure for crude fiber seen before. Well, In this matrix, in this table, we can see matrices, certified average, certified standard deviation, and statistical test results for the uncertainty of these matrices. The matrices were ordered by their average. Now we have here in yellow part, we have matrices which are the same. Here can admit and here can admit. Here milk powder and milk powder. Unground soybean meal and unground soybean meal. We can see that when comparing wheat flour and canned meat, there was significant differences in this uncertainty in them. When you see here breadcrumbs, here porridge oats and breadcrumbs, we can see difference significant of uncertainty between them. When we see canned meat, there were significant differences between uncertainty of them, but they have the same average. Here, in milk powder, safflower meal and milk powder had certified averages very near one from the other. But the F-test showed that their uncertainties were significantly different. The same happened for milk powder. Their averages were very close, and the result of F-test showed that these uncertainties different one from the other significantly. And this happens a lot of times. If you see here in the lower part of the table, you can see that several matrices presented significantly differences in uncertainties in the proficiency test. Well, now we have here another plot of the certified standard deviation per their certified averages. But here the averages were ordered. We can see here one interval, other interval. The intervals in black are intervals where the certifiers uncertainties different significantly one from the other. Então, so a lot of results of uncertainty which are significantly different here, and here. In fact, we had 7 intervals where this happened. And the methionine was excluded again. So when writing results, if I have one result here, which uncertainty will I use for express my result? This or this? Which one? How to select them? How to say what uncertainty will I use in this case? Here we have 30% of the scale for total win schemes. So we ask, it is valid to say that we have one uncertainty across the analyte scale? Well, the linearity is very used in the methods we use every day in our routine. Linearity definitions are several, but they are very, very similar. In Neuraken, linearity is defined as within the linear range, signal response will have a linear relationship to analyte concentration or property value. From each is its ability within a given range to obtain results which are directly proportional to the concentration of the analyte in the sample. By FDA 2019, linearity is the ability of method to provide an instrumental response or test results proportional to the quantity of analyte to be determined in the test sample. But linearity has to be checked too. If you see the figure 8, figure 8 shows the 95% confidence interval of regression. For instance, chromatographic measurements have a calibration curve that uses regression techniques, but the regression confidence interval is not constant. We can see that this interval is not made by two parallel lines. You can see in the figure 8 that at the right and the left, these lines opened. So you have not one uncertainty constant all over the interval of the standard concentrations. Doesn't matter which is the method. UPAC 2002 is very clear when it says we have to check the regression. And just in using this, you can see that the regression is, the confidence interval is not constant. So the uncertainty is not constant. Thus, cannot exist one unique estimate for uncertainty along the axis of the analyte, unless we make dilutions and reduce its range. UPAC says that precision very often varies with the analyte concentration. Typical assumptions are that there is no change in the precision with analyte level, or the standard deviation is proportional to, or linear dependent on analyte level. The assumption needs to be checked. Well, we are seeing here that the linearity, the standard deviation is proportional to the analyte level, even in proficient tests and for total N, which is one common analyte for food. We have to check the precision, and together with a suitable statistical test for difference in variance. It was we done here in table 5. So we conclude that the plot of certified standard deviation per certified average may incur errors. Uncertainty in chemical and biochemical food components ranged significantly in several tests. Uncertainty of chemical and biochemical food components ranged significantly along their axis, and not only from one matrix to another, but also within the same sort of matrices. There were some updates in standards, as we saw when they say to check the linearity and the precision. But they did not seem enough for scientific purpose, nor to express results of analytical and bioanalytical methods. We have here some reference used, Iraqan, FDA, Hamaker, Hempel, ISO, IUPAC, Symantec, Turkey, and Campton, classic of design and analysis of experiments. Thank you. It was a pleasure to say something about food quality for you. Have a nice day.
Thank you very much, Mrs. Elisabeth. That was an excellent presentation. I would like now to invite Mrs. Taiza Lopez.
Hello.
From the Rio University in Brazil. Welcome.
I can share my screen. I think she has to stop sharing hers first. Yes. Let me see. Yes, I can. Can you see my presentation?
Yes.
Yes.
Okay. So hello.